So in this video, we're going to talk about predicting the products. So this is some SN1, SN2, E1, E2 reaction practice, right? So we're going to give some examples, and you should be able to tell, okay, well, is it going through E1, is it going through E2, etc., and why, right? And so we're going to do this. We're going to do some examples and kind of give you some practice. So what if you're given this on an exam? Predict the product. Is this an SN1, SN2, E1, or E2 reaction? Well, I'm going to look. I have a secondary alkyl halide, right? So the carbon has only one hydrogen attached to it, right? And my nucleophile, which in this case will be the oxygen, it's not charged. So it's a weak nucleophile. This is actually ethanol. Right? So in other words, it's a weak nucleophile. I'm on a secondary alkyl halide. Now remember, we said that a primary alkyl halide, which the carbon contains two hydrogen, think of it as being really open to attack. So the more hydrogens you have on the carbon that contains the leaving group, the more open it is to attack. So if it's more open to attack, the reaction will proceed faster. In other words, when a secondary alkyl halide, okay, well, it's not primary, so it's not really open to attack, but it's not tertiary, so it's not really what you think of as being sterically hindered, right? So there's still a little bit of room for attack. Now, because the nucleophile is weak, this will be your classical SN1 reaction because I'm on a secondary alkyl halide, but my nucleophile is really weak. Had my nucleophile been really strong, like something that was negatively charged, then I would be looking at an SN2 reaction. So because this is an SN1 reaction, essentially we expect the bromine to leave, and intermediately we form a carbocation. There's my hydrogen, right? And there's my carbocation. In this case, I'm on a secondary carbocation. Essentially, the oxygen now will come in. So if I write this out, lone pairs from the oxygen will come in and directly attack. And that will give us the product. There goes my hydrogen. There goes the oxygen that now has a hydrogen, but it also has an ethyl group. Now, oxygen with two pairs of lone pairs and 3 bonds, that's positively charged. And the last step of the reaction, another molecule of ethanol actually comes in and acts as a base. So this comes in, takes off the hydrogen, put the lone pairs on the oxygen, and essentially we get the product, the final product, to be OCH3CH2. So this will be our final product. So not only we're predicting the final product, we're also going through the mechanism if necessary. How about this one? Would this be E1, E2, SN1, or SN2? Right? Well, DMSO, we know that DMSO is our solvent, and we say that DMSO is polar aprotic, right? So it's polar aprotic. In other words, polar aprotic stuff favors an SN2 reaction, right? So polar aprotic solvent favors an SN2 reaction. Now we know that sodium is positively charged, so it can never be a nucleophile, but we know that cyanide is negatively charged. So we know that cyanide is our nucleophile. So we have a strong nucleophile in the cyanide. We're in a polar aprotic solvent, so that also gives us the idea of SN2. And we're on a secondary alkyl halide, right? So the alkyl halide, again, is not really directly open to attack like a primary, but again, because your nucleophile is really strong, we could safely say that this would go through an SN2 reaction. So all occurs in one step. Cyanide comes in, attack, and we displace the chlorine. And so essentially, the product of this reaction would be this, right? let's have some more fun. What if you're given this molecule? And we put this in methanol. Now the directions here, I'm going to say assume that E, and E stands for elimination, right? So we're going to assume that elimination is minor here. Now the reason why we're assuming that elimination is minor here is because the reaction can actually really go either substitution or elimination. So we're specifically directing this question to, okay, well, is this an SN1 or SN2 reaction? Well, the alkyl halide that I have, it's on a secondary alkyl. The alkyl halide is on the secondary alkyl halide. All right. And my nucleophile in this case, which is the methanol, is not strong. So it is a weak nucleophile. I'm on a secondary alkyl halide. Right. So we should assume here. So this is your classical SN1 reaction. Right. The secondary alkyl halide, okay, it's not really open to attack, and our nucleophile is weak. Had our nucleophile been strong, like our SH minus or a cyanide minus, then we would be looking at an SN1 SN2 reaction in which, again, it's concerted. Right? So the first thing we know that happens in an SN1 reaction, the leaving group leaves. Right? So that leaves us with, there's our hydrogen. We're on a, in this case, a secondary carbon cation. Now, if we remember that we could get this carbon cation and a more stable carbon cation in doing a 1,2 hydride shift, right? So if we do a 1,2 hydride shift, right? If we do a 1,2 hydride shift, then this hydrogen comes in and satisfies this hydrogen here. Conversely, the positive charge now moves to a tertiary carbon cation, which again we say is more stable. So there goes my CH3, there goes my positive charge, and there goes my 2 hydrogens. That carbon is satisfied. Now my methanol, the oxygen portion, which contains the lone pairs, can come now and attack, since it's an SN1 reaction. So it's going to come in and attack, and that as a result gives you a CH3 that's still up. Right? Now, because the CH3 is up, we would expect that the OCH group, or the oxygen portion coming in, would be down. Now, we're not going to show stereochemistry here, and actually, just remember here, and let me put this in brackets, that here, this carbon is flat, so it's trigonal planar. So I really shouldn't be showing stereochemistry at this CH3 portion right here. So just remember that, right? So correct that. That carbon now is flat because it contains 3 bonds, so that's now trigonal planar, and so there's no stereochemistry. So no stereochemistry should be shown at this carbon here. However, I did, right? So that's just my correction to you. Right? No stereochemistry should also be shown here, right? So this should be just a single bond, but because I already did, I'm not going to erase it. Right? So now the oxygen comes in. It comes in with a hydrogen, and it comes in with a methyl group. It has a lone pair on it now, but remember, oxygen, 3 bonds, and a lone pair, we have a positive charge. The last part of the reaction, another molecule, methanol, comes in, takes all the hydrogen, puts it in the form of lone pair on the oxygen, and so essentially, showing stereochemistry now with our final product, we have our CH3 still coming up out of, but we have our OCH3 group going down. So this is your classical SN1 reaction. Again, we're also showing the reaction mechanisms. How about this one? What would be the product of this reaction? Well, I'm looking at a base, right? So this is an alkoxide, an oxygen chain, an oxygen with a carbon chain. So I'm looking at a strong base, an alkoxide, and the alkyl halide here is actually a secondary alkyl halide. Now, because this is a strong base, and the alkyl halide is a secondary one, then this is your classical E2 reaction. In other words, it is concerted, it is fast. So this would be your classical E2 reaction. Again, this would be your classical E2 reaction, right? So this is going to come in and take off a hydrogen adjacent to the carbon, right? It cannot take off any hydrogen over here, right? It's not possible. Why? Because again, there's really no hydrogens. There are only methyl groups there. So it only has one option to take off this hydrogen adjacently. It's going to form a double bond and then displace the chlorine. And so that all occurs in one step. And so this would be our final product. Again, an E2 reaction. How would we, what would be the what type of reaction would you expect this to proceed through? Predict the products. Well, I'm looking at a secondary alkyl halide, and okay, we know that our sodium is positively charged, or SH group is negatively charged, so therefore it must be a nucleophile. So we have a strong nucleophile because again, it is negatively charged, and we have a bromine, we have a secondary alkyl halide, right? So this is your classical SN2 reaction, all occurring in one step. Now remember that SN2 reaction show stereochemistry. In other words, what was R goes to S, or in other words, what was S goes to R. We're talking about the chiral centers. So in this case, we do have a chiral center, and so essentially SH is going to come in, attack, displace the bromine in one step. Now, essentially, the SH group is going to be going away now. And so this would be our major product for this reaction. Right? I'm not going to waste time to do the chiral center configuration, but you should see that if the reactant on the left, if the chiral center was R, you should see that now the product should be now S, and vice versa, right? So I obviously did not do the chiral center configuration, but do it for proof. So again, SN2 reactions show inversion of the stereogenic center. So that's something you should be very comfortable with. How about this one? Well, we know that sodium is positively charged, therefore oxygen is negatively charged. Now, we're dealing with a primary alkyl halide here, right? So this is your classical, we're dealing with a primary alkyl halide here, so this is your classical SN2 reaction. In other words, the carbon chain is really open to attack because it's on a primary, it is a primary alkyl halide containing two hydrogens, right? So we say that the more hydrogens a carbon contains, the more open it is to attack, right? And again, our nucleophile being our OCH3 minus is really strong, so we'll know this is occurring in one step. Again, it's going to attack the carbon, displace the bromine. So essentially, our product should be that molecule. So that's your classical SN2 reaction again. What if we did this one? Pause the video. Excuse me. But pause the video and try this one. Well, I'm on a secondary alkyl halide, right, where the chlorine is, only containing one hydrogen, and my nucleophile is really strong, right? This is your classical SN2 reaction again. right? All conservative. My nucleophile is really strong. That means, in other words, my nucleophile is really strong when I see a negative charge. And okay, my alkyl halide is not really open to attack because it's secondary, so we're kind of in the gray area. But because the nucleophile is really strong, this would be an SN2 reaction all day, every day, right? Now remember, because we are shown stereochemistry, we have to invert the chiral center, right? So this would be the final product of this reaction, right? Again, whatever is R goes to S, or vice versa. Whatever is S goes to R. So you can do the chiral center configuration and kind of prove to yourself that that's a classical SN2 reaction. Pause the video and try this one. Is this an SN1, SN2, E1, or E2 reaction? Well, I'm looking at the base, right? This is an alkoxide, right? I have an alkyl chain with an oxygen on it. It's a classical strong base. So this base is really strong. And I'm on a secondary alkyl halide. So because my base is really strong, I'm on a secondary alkyl halide. This would be your classical E2 reaction, all occurring in one step. Right? Now remember that the base takes off the hydrogen adjacent to the leaving group. Now we have these hydrogens, and if we did that, this would give a Hoffman product, and certainly that would be a product. But again, we're always looking for the most stable product, and so in this case, we're looking at the Zaitsev product coming in, taking off the hydrogen, forming a double bond, displacing the chlorine, and so essentially our product should be that molecule. How about this one? Try this one. Predict the reaction. Predict the product of this reaction. Is it an SN1, SN2, E1, or E2 reaction? This is a special case, and this is actually no reaction. Anytime you have an alcohol, OH group, and you're putting it in any sorts of salts, like so sodium chloride, lithium chloride, potassium bromide, it will never react. Right? So keep that in your mind. That's a special case in organic chemistry. Right? So salt and an alcohol really do not react. So remember to keep that in your organic chemistry minds. How about this one? Is this an SN1, SN2, E1, or E2 reaction? Well, I have an alcohol, and this is a special case, and I want you guys to recognize this anytime you come up on this in organic chemistry. Anytime you have an alcohol and an acid, right, so this is hydrochloric acid, this is your classical E1 reaction. And this is what we call an alcohol dehydration. So anytime you have an alcohol in an acid, this is an alcohol dehydration. Now, I want you to think of any acid as just really being H plus in solution. Right? So the reaction mechanism for this is actually important. So we're actually going to go ahead and go through the reaction mechanism. But this is your classical E1 reaction. In other words, I'm going to form a double bond. So the oxygen on the alcohol actually is a nucleophile, comes in and takes off and take a H plus, really, which is what acid is. Doesn't matter if it's HCl, HBl, HBr, or HI, or sulfuric acid, phosphoric acid. Again, it's still H plus in solution. So that is the first step in the reaction. This oxygen then essentially now has two hydrogens attached. It has now one lone pair. This is our classical positive charged oxygen, or positively charged oxygen. Now, essentially, we form water in solution. So essentially, we formed water in solution. Now, with this being the case, the water now leaves as a leaving group. So in the next step in the reaction, we've now formed a carbocation. So there's my positively charged carbocation again with one hydrogen, right? Again, or one hydrogen is here, we just didn't write it. Now this is a secondary carbocation, right? So essentially I could do a 1,2 hydride shift. A secondary carbocation, so I could do a 1,2 hydride shift. This hydrogen comes in and satisfy the positive charge. The positive charge moves over to the opposite carbon, right? So what I've now done is I put the positive charge in a tertiary carbocation versus a secondary carbocation. Now, because that is the case, in the last step of the reaction, remember we essentially formed water in solution, right? So because we essentially formed water in solution, water is going to come in and act as a base and take off the hydrogen adjacent to give us the Zaitsev product. Again, obviously the Hofmann product is possible here with these hydrogens, but again, we're really talking about the major product of the major products of these reactions. So it comes in, takes off the hydrogen, forms a double bond, and so we get the final product of this reaction to be something like this. And so that we would expect to be the final product of this reaction. This is your classical E1 reaction, in which we call alcohol dehydration. If could you predict what the product is, what type of reaction? Well, I'm on a secondary a primary alkyl halide, which contains 2 hydrogens, right? So it's really open to attack. My nucleophile is really strong, so I'm looking at a classical SN2 reaction, right? So it's going to come in, all occurring in one step, attack the carbon, displace the bromine. And so essentially, my product would be this. And I hope this video helps with respect to the practice for SN1, SN2, E1, or E2 reactions.